They were okay. They weren't that long, but they could have been.
Like the way you talk.
So I'm Racine for Rossmore Technology.
My favorite part.
That was really half the video.
Yeah, because they were all like 2 minutes long, and then his intro is 20 seconds long, and then he's just trying to rack up those views. He knows you got to watch at least like 12 of his videos then to figure out anything about assembly.
Yeah. But outside of that, they're actually pretty decent in terms of what they cover. They're actually pretty decent.
I thought they were, at least the first like 8 videos were super basic. If you had just given us the Word document that he was showing.
Oh, sure. I totally agree. But he usually does overkill on examples.
Sure.
Like, here's a trivial example, and if that wasn't enough, here's 4 more.
And the examples I didn't mind because he would do like odd cases.
Yeah.
Or whatever. I guess.
But as far as assembly tutorials go online, they're about as good as I could find.
Sure.
Some of them are pretty.
It's like the top hits.
Yeah. Plus, he has a lot of them, so he covers a lot of material on there. Well, he covers not necessarily a lot of material, but he covers all of the material. You know, because with an 8086 emulator, there isn't that much. In fact, we're going to build one, but we're going to understand what. Yeah, why not?
8086 emulator.
Yeah. Why is that a problem?
I don't say it's a problem. It just seems like either you're lying that we're going to build a full 8086 emulator. Didn't that take a little bit of time for them to?
Well, so let's think about that.
Yeah, or is it going to be like the program we made that's was a.
Well, we're starting it in the grad class tonight, but so if we think about writing an emulator, what do we need to be able to do? So let's just kind of think about the high level. We'll spend 5 minutes thinking about it. We're not starting it yet, but we're not there yet. What does it mean to be an 8086 emulator? Now that you spent last class getting the 8086 emulator installed, whether you're on a PC or Mac using Wine,
Basically just goes through the code and fills the registers, or shows you what's technically in the registers.
Okay. So at the end of the day, it's kind of a cheat sheet for registers, right? I mean, so when you're emulating 8086 instructions, you're kind of watching the registers change and stuff like that. The difficult side of it would be the flip side where you actually want to execute the code, right? So, when we talk about, 8086, we talked about a bunch of registers that we already have in there. We have, what are our registers that we know about? AX, BX, what's the high and low of those? AL, AH, BL, BH, so on and so forth. Okay, so then we have a whole bunch of flags, right? CL, CH, DL, DH. So those are our registers, and there's actually a couple more beyond that, general purpose registers, so let's leave it at that. So then we have flags. So we talked about just a couple of flags that are kind of commonly used, important flags. What were the couple that we talked about last class? Carry flag, CF, and zero flag. You weren't even paying attention, were you?
Apparently not. I don't remember those two.
You remember either of those? Did we talk about them last class? Were you here last class?
Yeah, pretty sure.
Did a new game come out this week? No? Nothing?
Bioshock got re-released.
What's up?
Bioshock got re-released.
Are you playing that?
Not a re-release. I ain't got time for a re-release. I already played those games once. I don't even see it.
I don't know. All right, so these are all of our registers. Some of these are 32-bit, some of these are 16-bit. Actually, these are all 16-bit or 8-bit, right? For these, if you were doing a 32-bit, you would have EAX in there, which is some of the examples we've seen, but not 8086. 8086 has AX, which are 16-bit registers, and then high and low of those, which are each 8-bit registers. So if you're writing an emulator, and you think about some of the commands that we know already. So what are a couple of commands that we have seen so far in looking at the assembly language stuff? Move. All right, we got the move command. Okay, what's another command we have? Add. Okay, jump. There's a bunch of different jumps, but let's leave it at that. All right, so just looking at these three, what does the move command entail? So the destination is always either a register or a variable, right? And the source is either a register, a variable, or a literal, a value, right? Okay, so to emulate that, what are we going to do? Well, we would probably create variables to hold those guys to make it look binary-ish. We maybe represent them as strings, something like that. And if we said move 11001111 into AX, well, we would set the string equal to that value. Display it on the screen, right? So everything's about just, these are variables, and we can store aspects in those. Now, what we might do is we might represent these four as 16 bucket integer arrays, where each bucket holds a 0 or a 1. What would be the advantage of representing those as integer arrays rather than implementing them as strings? Huh? Probably be pretty similar in size. It would actually be technically smaller as strings, but then you get the trade-off of the overhead of string. It's probably gonna be similar because string is Unicode, so you will actually only each character 16 bits instead of 32 bits for an int. Most ideal would probably be storing it as a byte array. That's the best we'd be able to do in Java. Even though we only need 0 and 1, we could technically hold -128 to +127 in there. But I mean, the real answer is if we store it as ints, we can do, it's then mathable, right? We can do mathy stuff with it, and it looks like we're going to sometimes need to do mathy stuff. All right. So one advantage is we can now add bit to bit without converting chars into their equivalent integers. We can also, if we deal with a 16-bit int array or short array or byte array, doesn't matter. We're just thinking about it as just numbers. We're not trying to minimize footprint here. And we need to represent the high and low of that. We can deal with the first 8 or the second 8 bits. So we can actually represent these guys just like they would actually be represented in a processor. We're just doing it in software, right? So moving things from variables into or moving literal values into a register should be pretty trivial. You know, maybe the more difficult part of an emulator would be dealing with variables. Okay, so if we're just working with kind of the math aspect of an 8086 emulator, you know, we would probably have literals going into registers or registers going into other registers and take the variable side out of it, because that means we then have to implement some sort of variable environment, which also really isn't a big deal for us. We would just have a string array with, you know, names and then a parallel array that just has the corresponding values, which are all going to be numbers. So that wouldn't be that difficult to deal with either. But ultimately what we're looking at is as you do moves and adds and things like that, the values in these guys are going to alter. And that's what we're really interested in seeing with the 8086 emulator. We want to see that, oh, after this one instruction, when I move this value into AX, here's the new value of AX. So let's jump into that real, where's my icon for it? There it is. All right, it's not going to give me a here. Hello world code example. Perfect. This is kind of a crappy code example for it, but that's okay. I'm going to delete like a large chunk of this stuff. This is color coding characters and stuff. Or actually, just so we stay consistent. Hello. I think it's going to give us the exact same one. I think this will be good enough for us here. Oh, that's interesting. Am I not going to be able to? Oh, yeah, I can. Can I make this bigger? Or is this as big as? Can we read that? Is that okay? All right. So I'm going to get rid of. Let's just make sure this works first. Oh, because it doesn't know about EAX and those guys. That's fine. I'll leave those variables down there in case we want to use those. So if I move AX 5, let's say something like that, and I'll go ahead and emulate this. There are errors. All right, I guess I need to do the tiny thing. There's our move AX5. We really don't care about the rest of this. All right, so we're sitting on this line right here, and now I can do a single step. So we look over here at the AX register, and right now at the high and low are both 0, 0. Now these are represented as hex values rather than binary values, to save some space, and we'll talk about that here in a second. So I'll go ahead and do a single step over that, and we notice we get a low value of 5 in there. Now, I put 5 decimal in here. If I wanted to put hexadecimal in there, I think I put an H. If I wanted to put binary in there, I put a B after it. That was, I think he explained that stuff in the videos. Okay, so we just saw the value of AX change. Okay, let's go back here. I gotta kill this. I killed this. So if AX is a 16-bit register, we'll just start with this. What is the largest value that will fit in a 16-bit register? Go ahead. Okay, 65,535. Okay. So we'll put 65,535 like that, or we can go in and we can put 16 ones and put a little b after it. That would have worked out okay as well. All right, so let's go ahead and run this. Step 1. So here's our FFFF. There's your evidence that it's a hexadecimal number, right? So let's jump over here real quick. And let's look at number representation. All right, so let's deal with 16-bit register here for a second. Now, when I say something's a 16-bit register, what does that mean? What does it mean to be a register that's capable of holding 16 bits? Kind of like an array, right? It's an array with 16 buckets in it. Each of those buckets, I can put a single bit, a 0 or a 1. I can't hold any more than that in that register, because that register can only hold 16 of those. Okay? So that means now we're going to be talking about signed and unsigned numbers here as well today. And we're going to talk about 3 different ways of representing those that you'll also read about. I think you read about it a little bit already in the original assembly tutorial, and you'll read about it in the next section of the book. So for number representation, this is just generically speaking, and let's just think about positive numbers for right now. I have 16 bits to work with, so I'm thinking about large positive numbers. So my value for 65,535 will be a 0 at the beginning. Don't ask me why for a second. And the 15 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? So that is a positive 65,535. Okay? Actually, if we just deal with positive numbers only, unsigned, we'll do it like that. All right, so that's 65,535. Now, if I want to convert that, so that's binary. So we'll put a little b after that. Now, we've already said this is 65,535 from that. Now, how did we get that? This is the ones place, 2s, 4s, 8s, 16s, 32s, 64s, 128s, 256, 512, 1024, 2048, 4096, 80, blah, 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 blah. Just keep multiplying by 2 for the last couple. Then you add all those guys together and you get 65,535. Okay, the range of values is 0 to 65,535. So 65,536 unique values. Okay, so one thing we want to start bending our mind towards here is the idea of number representation. Math is often used, so we often can calculate the value, but nothing says that we have to treat it in a mathematical way. All right, just like we can create associations, right? I can say A is the value 7, B is the value 6. Even though that's not a mathematical thing, if I say B, you can map it to the value 6 inside your head, right? Okay, so we can deal with these registers in different ways. Just sometimes we need to know that we're not going to do math with those values. All right, so this is binary, this is decimal. Now we need to do the hexadecimal version of that. So previously, I've taught that the way to convert a hexadecimal value, so 65,535 to base 16, or let's say to hex, we would take the 65,535, we divide it by 16, 65,535 divided by 16 gives us 4095. 4095, and then that's going to be remainder 15. How did I get that? 4095 times 16 is 65,520. 65,535 minus that is 15. That's the remainder. That's left over. So let's look at that again. If I take 65,535 and I divide it by 16, this is the whole number value I get. There was decimal places after it, right? That's the integer value I get. But now I have a remainder. What's left over to get me back to 65,535? The way I get that is I multiply this guy by 16, which gives me 65,520. The difference between this number and this number is 15. That's the remainder that was left over. In fact, 16 almost went into 65,535 4096 times. Came one value short. Almost went in there another time. Make sense? Okay, then we'll divide this guy by 16. So 4095 divided by 16 is 255, almost 256. So that's 255. Is this a tab? Nope. Oh, oh. Remainder 15, because 255 times 16 is 42,330.
That's not right.
Did I do the math wrong? Oh, look at that. Is 4080. 4095 minus 4080 is 15. That's how much we take to get to the next value. Make sense? Now we keep trucking. Divided by 16. 255 divided by 16 is 15. Remainder 15. And 15 times 16. 15 times 16 is 240. 240 to 255 is 15. Remainder. So there's that 15. 15 divided by 16. How many times does 16 go into 15? 0 times. 0 times 16 is 0, with remainder 15 to get us back to 15. And we know we're done because we're at the 0. Then we read our answer from bottom up. So our answer is 15, 15, 15, 15, where this 15 is this guy, this 15 is this guy, so on and so forth. But now 15 is not a legal digit. Well, it is a legal digit. It's not a legal digit. It's legal digits. It's not a legal value in the hexadecimal number system. What are the legal values in the hexadecimal number system? Close. 0 through 9, A through F. Okay, 0 through 9, A through F. So they all have to be one character, right? One character. So 15 is actually the value F. So 65,535 is actually equal to FFFF. And we see that represented right here. FFFF. Make sense? Now, why did it do that rather than show us 8 zeros and ones followed by 8 more zeros and ones? Well, is it really? Is binary necessarily easier or harder to understand than hex for us?
Easier to display.
Easier, definitely easier to display. And when you say cleaner, what do you mean by cleaner? Easier to read, like
Yeah, there's
less intimidating to read at first until you start freaking out when you realize it's still more intimidating than decimal.
Well, 16 bits is 4 characters, whereas like with binary it's 16.
Who?
I said with hex, like it's 4 characters for a 16-bit register, and then for like binary it's like 16. Like that's harder to read.
Oh, fine. Fine. So we're going to say that these numbers are equivalent. This is the binary equivalent. We're going to say that this number is easier to glance at than this number. Fair enough? But they're both kind of cryptic to humans. We'd rather just say 65,535. That might be relatively meaningless to us, but we're used to looking at stuff that looks like this. Make sense? Okay. So this would be a hexadecimal representation of 65,535. This would be a binary representation of 65,535. So yeah, here is our binary representation of it right here. Now, we went through this whole big rigmarole to convert this guy to hex. What if I wanted to convert this number, I'm sorry, other way, B to hex? I want to convert this 16-bit binary number to hexadecimal. How would we do that? Well, you got to write the program with the computer. You just use the Google.
Can you group these into,
Are you answering your own question?
I've been told I can.
All right, I'm gonna stick with you then.
I can give you the first part, someone else can do the grouping.
You've lost some of your confidence. It seems like ever since
He's been calling me out.
ever since the student of the month loss. That's been a.
Been eating away at me.
Did you guys see the? Was that a couple nights ago the Emmys, where Jimmy Kimmel? It was Jimmy Kimmel the host, I think. Well, on the Jimmy Kimmel show, there's this long-standing joke with him and Matt Damon.
Yes.
That, you know, I guess for a while, like Matt Damon was supposed to be on the guest on the show, but then would get bumped at the end of the show. I'm not even sure if it's real or fake. Like, I think there might have been real animosity, and then they turned it into like a joke. But there's this ongoing thing if you follow the show. Well, I guess Kimmel was the host. I just saw the YouTube video. I didn't watch the Emmys, but I guess Kimmel was the host, and he was getting ready to announce the next category. But the previous category, which I think John Oliver won, Kimmel was also like put in the finals for, and his show lost. So he didn't win the award. Well, so when Kimmel's up there giving like the announcement for like the next award, probably I guess introducing the next people who are going to come up, Matt Damon comes wandering onto the stage and just said, "It's like, oh, hey Jimmy," and it's like, I missed the last category. Did you win?" They had the whole back and forth. It was kind of funny.
That was trending on YouTube last night.
Yeah, I saw it on there. Yeah, so I thought that was pretty funny. Did you know the backstory? Yeah,
I
that's.
was all confused.
Oh, it's extra funny if you kind of know the. I mean, it's like a multiple year. I want to say like a 5 or 6 year backstory, where that this has been going on, the whole Kimmel versus Matt Damon thing. All right, so you're helping him cheat?
Yeah.
Oh, we're done with you people. All right, somebody else. I don't like you. Actually, I'm pretty confident you know the answer. So how can I conveniently convert this guy to this binary number to hexadecimal? Now, right off the bat, as human beings, we look at this and say, well, I'm out of here, right? Okay, this is not a fun thing for us to do. But we're also going to recognize as we look at this why hex and binary are convenient values. Go ahead.
Maybe somewhat off, but at least we'll be on the right track. Don't you group them into fours? And take each of those four and change that to the next value.
Okay. First of all, what's that guy called? What's a 4-bit number called? Nibble. It's a nibble. That should have been a quiz. Would you have missed it?
A nibble, that's made up for sure.
I think I said it at least 15 times last class. Easily.
You said it like twice at the end.
No, 15 times because that would be the. Well, everything that comes out of my mouth is gold.
You're supposed to listen to all of it?
All of it. Not just listen, but memorize it. That's why.
Jimmy Kimmel thing,
that-
was gold right there.
Could be a quiz. I mean, isn't that the thing? That students are responsible for everything that's covered in class. Random stuff, wrong answers, all of it. So then it gets to this thing where you're not sure if it's a wrong answer or a right answer. I might ask, what was the wrong answer from? All right, so if I just threw this number in front of you, this 4-bit number, this nibble in front of you, and I told you to convert that to decimal for me. This is the 1's place, the 2's place, the 4's place, the 8's place. So 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So this guy is a 15. 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 15 doesn't exist in the hexadecimal number system, so we actually represent a 15 as an F. Make sense? A little bit easier.
Octal split into 3.
Yeah. So if I asked you to do it to octal, base 8, you would do these in groups of 3. So now, why did I just arbitrarily choose groups of 4, groups of 3? Go ahead.
Because the maximum it can give you is from 1 to 15 for 4.
Okay.
Because if you had 16, it'd just be 0.
Let's just do y. So if I have base 16, base 8, well, let's do base 10, base 8, base 10 is not really used. Base 8, base 1, base 2, I'm sorry. What are the legal values in base 16? You already mentioned it. It's 0 through 9. And A through F. And really, this is 10 to 15 in decimal speak inside of our head. We just converted it. Okay? So the unique values here are 0 to 15 for base 16. The unique values for base 8 is 0 to 7. The unique values in base 2 are 0 to 1. So it's always going to be 0 to the base minus 1. Those are the values that are allowed in that number system. Okay, we want to start thinking about these guys as systems. So why did we choose, we already solved for 16 bits, we chose 4 bits. For hexadecimal, rather, we chose 4 bits. For base 8, we chose 3 bits. Why 4, why 3? What is the largest value in the hexadecimal number system? F or 15. Yep, F or 15. Okay, so F would be the hexadecimal character. 15 would be our decimal equivalent, right? So doesn't matter which of those you think about, just understand that they're the same value in 2 different number systems. All right, so the largest value in hexadecimal would be 15 decimal. Okay, not the largest single character value in hexadecimal. So that means we need enough bits to represent that value, right? Can you represent the number 15 in 3 bits? Can we do it in 4 bits? Do we need more than 4 bits? Or is 4 bits the perfect fit? Yeah. So with 4 bits, we can represent the value 0 to 15. Exactly. Make sense? In 3 bits, where we have the 1's place, the 2's place, the 4's place, we can represent values between 0 and 7. That's why we choose 3 bits for our groupings if we're converting to octal. You see how those are convenient groupings if we need to move things from one number system to another when your base is binary? Similarly, how would I convert FFFF from hex to binary? Okay. Well, right off the bat, I know I'm going to need how many bits to represent this value? How many characters are in this hexadecimal value? 4 characters in this hexadecimal value, and I know I need groupings of 4 bits for each of them. Okay? Even if it's a small value, so let's say this was 1 FFF. Could I represent the number 1 in less than 4 bits? Sure, but I need to create a numeric space big enough to house the whole hexadecimal system. All right, so each one of these guys is a 4-bit number. So that means right off the bat, I'm going to go and create some bits. 1, 2, 3, 4, that's for one of them. 1, 2, 3, 4, that's another one. 1, 2, 3, 4, it's another one. 1, 2, 3, 4. That's the last one. Then I'm going to convert each of these guys to the value of that. So 1, 1, 1, 1. And here, if we want to have fun with numbers here. Let's change that to a A and change this one to a 3. 3F, AF. All right, so here's our F. Now we need the number 10. So that is 1's place, 2's place, 4's place. So this is 8 plus 2 is 10. And this guy is going to be F, 1, 2, 3, 4. And this guy is going to be 3, just like that. And just take the spaces out. This is the binary equivalent of 3FAF. Does that make sense? So one thing that's going to be very important for us is we need to be very comfortable moving between bases. And really the hardest base for us to move in and out of is decimal, even though that's the base we're most comfortable with. Moving between hex, octal, and binary is actually pretty easy because we can do the little grouping trick. The second we move to a decimal number, the grouping tricks stop working. Okay? All right, so getting back to what we were talking about here, we loaded 65,535 into AX. Similarly, we could have said 1, 1, whoop. I guess I need to close this, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Load that value in there, emulate it, step once. We see we get the exact same value in there. Okay, but I put a B at the end of this guy to designate it as a binary number. Okay, so we have our FF in there. Two different ways of us representing the same value in a different number system. Now, let's close this. I'm going to say add AX, comma 1. So I'm going to add 1, which if we don't put any designation on it is assumed to be a decimal value, right? So I'm going to add a 1 to this big number. Let's go ahead and switch it back to decimal for us. So 65,535. All right. And remember, the general syntax for assembly is this is our destination register. So when we add 1, we're going to be adding this value to this register, storing the result in the AX register. Make sense? And 1 here is going to be treated as a 16-bit value. Why?
Because the register is 16-bit.
16-bit. So that 1, it's as if I said this. It's as if I said that, which is the number 1 represented as 16 bits, even though that's significant overkill for what is required to represent the number 1. Make sense? And we can see that if I just say move 1 in there, and I take out this line, and then I emulate it, when I step by 1, there's our 1 in the low bit. We know this is 1 hexadecimal because we've already been trained now that those are hexadecimal representations of our values, mostly because they have a smaller footprint. And secondarily, we've kind of claimed that, oh, 1 is easier to read than the other. The reality is that they're all equal. It doesn't matter whether we say the same number in binary or hexadecimal or decimal as long as we've done the conversion, right? They're the same value, just in different languages, if you will. Different number systems. Okay, so let's go. Huh?
It has a converter.
Well, what do we need a converter? We can just do it ourselves. Did I introduce it yet? I haven't introduced it yet. That's not I mean, you could use it for homework or something, but for a quiz, you can't whip out the 8086 emulator and say, okay, time to go. Now, you could pull out one of your old Java programs where you wrote a converter. That's technically a tool that you built. That's been introduced.
So you're telling me if I make my own converter, I can use it on...
I'm telling you that you've already made your own converter.
So I can use the converter that I've already made on quizzes.
Well, potentially, yeah. I'm okay with that. You show me the source code.
Okay. Well, you said you know we already made one, so do I have to show you the source code?
Yeah, I want to see that it's the one that you made for my class, because that would technically be introduced by me. Not like, oh, I made the Google one.
Yeah. I'm not gonna go try to find it. It's probably wrong anyways.
What do you mean? Everybody in here should still have their binary converter code.
Yeah, keep it locked away in my memory box.
Well,
Right next
given
to
that
Towers
you,
of Hanoi.
hold on, given the fact that you couldn't remember the stuff we talked about last class, you probably should
Yeah, maybe.
keep some of this stuff locked away. So maybe the next quiz should be write a decimal to binary converter program in Java. 5 minutes.
Recursion, no recursion.
It doesn't matter.
Using only forking processes.
It's no shared memory.
Yeah, no shared.
That's actually a really easy problem to write in Java.
What? The converter?
Converter, yeah.
Oh, sure. But 5 minutes? I don't know about 5 minutes.
Oh, yeah, especially from the person who didn't remember we talked about nibbles.
Yeah, exactly.
We're getting a little tired of this, aren't we? Yep. So we got to assign somebody to be the
This is why you didn't listen to me.
Yeah.
this is what?
This is why you didn't listen to me.
All right. So when I add 1 to 65,535, so we'll go back to our 1 here. And the answer to that question was why is this guy treated as a 16-bit value? Is because my destination register is a 16-bit register. Okay, and the source and destination have to be the same. And since I'm using a direct value, or your book probably calls this an immediate value. Have you read something like that at some point? They probably call this an immediate value. Go ahead.
How do you know the register that you're moving to is a 16-bit or a 32-bit?
Because we've introduced AX as being a 16-bit register. It's like given information. In the 8086 architecture, AX is a 16-bit register. AH and AL are the 8-bit halves of that 16-bit register. Yeah, so you have to know the architecture. So it's not like you have to guess. All right, so since this guy is a 16-bit register, this guy is going to be treated as a 16-bit immediate value. What do I mean by immediate value? Why would we call that immediate? Yeah, we don't have to go and look it up someplace. It isn't it in a variable, or it's not in another register where we have to go and retrieve it. It's here. It's immediately available to us, and we can just immediately use it. All right, so we're going to add this immediate value 1 to the current context of AX, storing the result back in AX. All right, what do you suspect we're going to see? So we already saw that after this first line of code, AX holds FFFF. So what's going to happen when we add 1 to that?
Gonna show an error or something?
Okay, tell me why it's going to show an error.
Because it's over the maximum amount.
Okay, so it's the value that we're going to get out of that, so we'll speak human, right? 65,536 is what we're going to get out of that. So, that's easy enough for us, right? 65,535 plus a 1, 65,536. Now, how many bits will it take to represent 65,536? You already told me we don't have enough, right? So, pretty good guess is going to be 1 more bit than we currently have, so 17 bits. So 65,536 is a 1 followed by 16 zeros. All right? But I only have 16 bits to work with. So you're saying that maybe we'll get an error. All right. Now the reality is we're definitely out of space. Okay. Now we introduced a couple of flags that let us know when stuff happens. Okay. One of those is the carry flag. All right. So let's go ahead and run this. So we'll go ahead and do a single step. There's our FFFF. Now we're on the line that says we're going to add 1 to it. That guy went to 0. And now I need to show the flags. There's our carry flag is 1. Now let's start this again just so you can see what the initial value of the carry flag was. Initial value of the carry flag was a 0. Put the FFF in there, still, it's a 0. Now it became a 1. 0 flag also gets set, so do some of these other flags, but let's focus on just the carry. Okay, carry flag says whatever you were just doing has a leftover. We have something after that that's left over that didn't fit. Okay, and since we're always dealing with 1s, that carry flag also represents the 17th bit, right? In our little math problem right here. We added 1 to something that didn't quite fit, so that spillover was our carry bit, which is a 1. So that's our far left bit of a 16-bit register, giving us the fictitious 17th bit if we happen to want to use it. Sometimes we care about the carry bit. Sometimes it means something to us. In this case, we might say, oh, the value is 0 in here. Therefore, since the value is 0, and why is notice the 0 flag is set? Why is the 0 flag set? Because the result of the last arithmetic instruction resulted in the destination register being a 0. So 0 flag is set. So if after I do that add, the arithmetic instruction, I look at the 0 flag and say, oh, this guy's set. That means whatever I just did broke that register. We can think of it as breaking that register, but really it's overflowed that register. It didn't fit in the register. Therefore, I must have something else. Now, let's keep with this example for a second. When the 0 flag is set after an arithmetic operation like add, I actually know that it only went over by 1. Let me show you what I mean by that. Let's say I add 2 here. Okay, what will the result of 65,535 plus 2 be? 65,537, which is
0, 1.
what's 65,537 in binary? We're going to have a 1. That's the 65,536 place. Then 15 zeros, and then a 1. So in terms of AX is going to be 15 zeros and a 1, i.e. not 0. Let's just see it, and then we'll break it down. So there's the FF. Then I'll add 1 to it. Okay, so that's the 1, 0. Oh, actually, it's 1, 1. Look at the flags. 0 flag is not set. Carry flag still is set. Okay, and why is that? Let's look at it.
How did you add 1, 2? Was that adding 12 or was it?
Oh, it was adding 1. Hex 1 and binary and decimal 1 are the same value.
Oh, you added the hex right there?
It didn't matter.
What's the, well, you did 1 space 2.
Did 1 space 2?
You're at AX.
Oh! I just wrote bad syntax. It just happened to ignore this. That's what I mean to do. See, I said you got to pay attention to all the bad answers too. That's a quiz now. All right, so I'm adding 2 to that value. We still got the same result. It just ignored the intermediate value there. So if we look at what happened there, let's go.
It's a different result.
Huh?
It's different.
We'll still have the carry bit. It'll still not be 0, but it'll be the 1.
Yeah.
Yeah. So it's, if you want to see what he's talking about, it won't be the B thing. It'll be literally a 1. There's our 1. Okay, let's see why it's like that. So we have a 1 with a carry flag set. Make sense? Because we had an overflow from the last arithmetic operation, but the resulting destination register, in this case AX, did not equal 0. It still has a value in it. How did that happen? Well, we had, what do we have? 65,535. So we had 1, 2, 3. So that's 65,535 in binary. All right, and we're adding 2 to it. The result is, let me give myself placeholders, please. 1 plus 0 is 1. 1 plus 1 is 0, carry the 1, 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 blah, 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 0, carry the 1, and that 1 gets thrown in our carry flag. So 1 plus 1 is 0 with an extra 1 up here. 1 plus 1 is 0 with an extra, well, this is 1 plus 1 plus 0 is 0 with the carry, 0 with the carry, 0 with the carry, all the way down here till we have our last carry. 1 plus 1 plus 0 is 0 with a carry, but now we have no place to put it. That's when this flag gets set. That make sense? Go ahead.
Would it be accurate to say that if you're adding 2 or more to the maximum amount, that it would actually reset the bits to 1?
No, because what if I add 3?
Would it be different?
It would definitely be different. 3 would be this value. So 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is what?
You carry the 1.
That's 1, carry the 1. Carry, 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 carry. So this is actually the value 2, not the value 1. So we add 3 to it. Same thing, 65,535 plus 3 is 65,538. What's the binary version of 65,538? It's going to be a 1 followed by 14 zeros, then a 1 0. So emulate. There's our moving the biggest number that we can into AX. There's adding 3 to it. There's our 2. And our carry flag is set. And the 0 flag is not set because AX doesn't hold 0. Make sense? So we're always adding. So it's not a 1 or nothing in that far right register. It's whatever the value is. The reason it was a 1 here is because the math dictated that this should be a 1. Okay, if I added 4 to it, that's 1, and then that's 0 carry. So this would be a 3 here with a carry bit.
So if it was like 7 over, then it would be 6, technically?
That's how it would end up working out,
Yeah.
yes. You're right. All right, so does that make sense? How those flags can help us when we run out of space on our registers? So we have to keep in mind that we have this finite amount of stuff to work with. And when they overflow, when we try to put 17 bits in something that can only hold 16 bits, same thing like when you're trying to fill a glass with soda or something like that, and you have a bottle you're emptying into the glass and you're convinced it will fit. And you get that surface tension moment, and then you have the, oh, it doesn't actually fit moment. That's the carry flag. when it actually spills over and we don't have enough space. All right, so these are our, well, we're mostly interested in these two flags for right now. Okay, so if we had done something and then we asked the question, is the 0 flag set? Just let's go back to when the 0 flag is set here. That's when I added 1 to it. We'll emulate that. There's our first step, FFFF. Second step is now it's 0 with a carry flag. Now the 0 flag is set, carry flag is set. When that 0 flag is set there, what does that tell us? How would you interpret that in English? What is the fact that this carry flag and the 0 flag are both set after an arithmetic operation? Okay, yes, but specifically what does it mean? Because we just saw several examples where the 0 flag was not set when we went beyond.
You're exactly one.
We just went over. We just went over, which effectively tells us that we need 17 bits to represent the new number, right? We're only 1 beyond, okay? And the fact that we just went over may be meaningful to us depending on what we're trying to do. Go ahead.
Does the carry flag get reset if you keep stepping in the program? Or
Does the carry flag get reset?
like if you go over, how long does the carry flag?
Oh, I understand what you're saying.
Yeah.
So if I do another line, move bx comma 4, let's say, something like that.
Yeah.
And then let's just leave it at that for right now. We'll run this. Let's show our flags. So there's our FFFF. There's the 0 with the carry flag. Flag stays.
Okay, then what happens if you fill that register again, like overflow it again?
Yeah, so how does it know which register the carry flag goes to?
The last arithmetic operation. So here, let's just go back here.
Okay, so since that.
Actually, you know what? It's actually a better question than I thought. Hold on, because technically A is the accumulator register. It lends itself to arithmetic operations. I think the carry flag will still get set here because this really comes down to is how does the add operation behave? So my understanding is that the add operation behaves. The flags show what was the result of the most recent arithmetic operation in our little world right now because we only know about arithmetic operations, okay? Regardless of what register it happened on.
That's not attached. Those aren't attached to any registers. Those are just.
That's my belief. So I believe it will get set here. Even though I've advertised that the AX register is technically, we called it the accumulator register. It's the one that lends itself to arithmetic building up stuff. All right, so it would make sense for the carry flag to only be associated with that, but I believe it's associated with all the arithmetic instructions, so it's linked to that, not to the register. Let's see what the scoop is. So there's our FF in BX. There's our 0, 0 in there, and the flag did get set. Yeah, so it's linked to the arithmetic operation, not to the actual register. All right, so it is accurate what I said that the carry flag, and in this case the 0 flag, as they relate to arithmetic operations, add, subtract, inc, there's an increment operation, it gets set based on the most recent one. And let's actually continue to prove that based on, so let's go back to AX for the second part here. So let's move into AX, the current value of BX, which we know is 0, right? And then we're going to add BX 1, which should give us, actually, let's, I'm lying because you want to see the flag reset. So let's add 5 into AX, and then let's add 1 to 5, which is not going to be a carry, right? So first line, biggest value into BX, add 1 to it, should give us a 0 in BX with a carry. Then we'll move a 5 into AX, BX is still its 0 with a carry. Then we'll do an add, another arithmetic operation on BX, adding 1 to 5, which gives us a 6, which is not going to overflow an 8-bit or a 16-bit register, right? So the thought would be that because carry flag is associated with most recent arithmetic operation, that carry flag should switch back to 0 as a result of our second add here, because a carry bit did not happen. Go ahead.
Wouldn't it be add BX, comma, AX1?
Well, it depends what you're trying to do. I mean, in this case, these are two completely separate things. I'm moving this value into this register, then I'm adding 1 to it, storing the result in that register. That gives us a 0 with a carry flag. Now I'm starting a brand new math problem. I'm moving the number 5 into AX. BX may as well not even exist to us right now, other than the fact that it had already set the carry flag. And then I'm adding, I get what you're saying. That. Yeah, see? I tried to trick her and I didn't. Then she tricked me. That's not very nice. So I'm adding 1 to AX. That's actually good. That means you're understanding. All right, so 1 to AX, that should give us a 6, which will fit in 16 bits easily. So carry flag should not be set after this most recent arithmetic operation. Let's emulate it. There's our FFFF. There's our 0 with the carry. There's our 5 into AX. And then there's our 6 in AX, and the carry and 0 flags have reset. Make sense? Those guys are related to the most recent arithmetic operation.
So now we don't know that one of our registers is over anything, right? BX is still...
We know that the register associated with the most recent arithmetic operation didn't have a 0 and didn't carry. We've lost track at this point of anything that happened with AX.
Okay. So if we were to look at AX right now, we're moving into a new one, would the carry flag be re-registered?
Moving it, no. Performing an arithmetic operation on it, yes. So if I add 1 to AX again.
So what I'm saying is it didn't, AX is filled up with nothing but zeros, right?
Correct.
So when we go back to that,
how do you know there was ever a value there?
Yeah.
You don't. Which actually leads to my next question. What's the purpose of the flags? Specifically, carry flag and 0 flag. Not just error checking, but let's take the error part, checking. So this is for conditional logic, right? After I do an arithmetic instruction, if I care about the current state of the registers before I start screwing with them, I really need to go and ask, what's the current state of my flags to kind of know what just happened? And do I need to do anything as a response before I start futzing with other flags? That make sense?
So the computer won't care at all. That's on you.
Zeros, yeah, I mean, the state of AX, sorry, let me stop this. The state of AX after all those instructions, from a computer's perspective, is literally identical to the state of AX right now before I've done anything. It's filled with zeros. And the only thing that had changed was at one point in time, our carry flag was set and our 0 flag was set. So we had an opportunity between instructions there to check the state of the flags to find out, was there anything interesting as a result of my last arithmetic operation? And do I care? Is there something I want to do because of that interesting thing? Okay. Do I want to take one of my, well here, so let's, before I answer this, in 8086 instructions, I'm going to do the step. I'm going to do the step. Okay. In 8086 instructions, I've advertised that 32-bit registers do not exist. It's a 16-bit processor. Okay? Does that mean that 32-bit values do not exist on 8086 processors? So if we go back to the 8086 days, does that mean I couldn't have held values? I couldn't have worked with numbers larger than 65,535?
Wouldn't you be able to use it or do something with it in between so when you had that carry flag, couldn't you tell what number it was based off of that? And the
Okay.
number that's currently in
So
there?
we had our 65,535. We added 1 to it. That gave us 0 with the carry. So our 16 bits are filled with nothing because we really need a 17th bit. But I'm on a 16-bit processor that only has 16-bit registers. How do I represent the number 65,536 on a 16-bit processor? Use 2 registers. We're MacGyver, right? Hey, you got to use the tools that are laying around you in the garage. If the architecture didn't hand you a 32-bit register, you got to make one. Like, well, I need a 32-bit register. Cool. I just happen to have another one laying around over here. Hopefully it's not being used for something else. Okay. I could also take a half step, right? I could use one of the 8-bit half registers of something to give me 24 bits instead of 32 bits, right? Okay, so I have some flexibility to represent larger values, but when I try to represent larger values, I also then introduce some issues in that I've effectively lost a resource, right? I'm using one of those registers, one of our 16-bit registers, or half of one of our 16-bit registers, to store this extra big number, which takes away a resource that I might want to use for something else. That makes sense? All right, so we still have to work with the tools that were provided here. All right. Let's see here. We're at 25, right? Okay. All right, so number conversion stuff. So this all makes sense? We're getting a decent feel for how this emulator kind of works, how it shows us. In using this, we really care less about the output of our program. So we kind of look at the Hello World assembly program as our that de facto starting point, just so we can appreciate how much more complicated displaying Hello World in a low-level language is than displaying it in Java or C# or something like that. So Java is system.out.println, C# is console.writeline. Many languages just print, whatever. It's not the crazy wall of text that goes into the Hello World in assembler. But what we really care about is regarding assembler in here is we're trying to understand how computers are organized and how the architecture works. So we really care less about the final result of what does this program do anything meaningful. We're just doing some mathy stuff here, right? But we care more about how does the state of our CPU change on a per instruction basis. Does that make sense? Because this tells us at the micro level what's happening to our CPU. You know, when a register overflows, how can we react to that? That kind of stuff. All right, so let's look at the book here. That's not our book. Okay, so we are on, I think your last reading assignment was through 2.3, correct? Okay, so we want to look at, let me look at the exercises. All right, so we want to read 2.4, 2.5, 2.6. And then I'm going to give you a couple of exercises to do, but I'm not going to give you any exercises dealing with the MIPS processor. As you go through the book, do those little quiz things, because when we're looking at MIPS versus 8086, you're looking at stuff that's pretty similar. But I don't want you to spend too much time like extra drilling the two, because then you'll get confused between them. So I probably won't give you any exercises dealing with MIPS. It's possible I would take one of their questions and say, do this as 8086 instead. So let me look at the exercises. I'll probably give you 3 or 4 questions based on those 3 readings. That makes sense? So the reading will be 2.4. 4, 5, and 6. So these 3 sections. So the logical operators are going to get us up to the place where we can start asking questions of those flags, that kind of stuff. And then there'll be some exercises to work on. I'll put those up this afternoon. All right? Questions, comments, concerns, bribes? All right, I will see everybody on Thursday.
That's a meeting happening this week?
It should. I gave him your schedule.